In this video, we'll talk about various identities, the double angle identities, the half angle identities, and the reduction formulas. These identities all have to do with re-expressing trigonometric functions at one angle in terms of another. For example, the double angle identities all involve evaluating a trigonometric function at the angle 2 theta and re-expressing it in terms of the angle theta. The reduction formulas allow us to reformulate expressions involving trigonometric functions to the power 2 as trigonometric functions to the power 1, but the trade-off is that the angle goes from theta to 2 theta. But the reduction formulas allow you to reduce the exponent on the trig functions. Sine theta squared, cosine theta squared, or tangent theta squared, all of these can be re-expressed in terms of cosine of 2 theta. The half-angle identities allow us to re-express sine, cosine, or tangent at theta over 2 in terms of the angle theta. All of these can be re-expressed in terms of cosine theta. We have three categories of identities, all of which are closely related to one another. We'll discuss them each individually. Let's start with the double angle identities. The double angle identities show us how to re-express sine of 2 theta, cosine 2 theta, and tangent of 2 theta in terms of trigonometric functions evaluated at just theta. For example, sine of 2 theta can be evaluated in terms of sine of theta and cosine of theta. Same with cosine of 2 theta. Tangent of 2 theta can be evaluated in terms of tangent of theta. Let's look at each of these identities. Sine of 2 theta is equal to 2 times sine of theta times cosine of theta. Cosine of 2 theta is equal to cosine theta squared minus sine of theta squared. We can also write cosine of 2 theta as 1 minus 2 times sine of theta squared, or 2 times cosine theta squared minus 1. Tangent of 2 theta can be written as 2 times tangent theta divided by 1 minus tangent theta squared. How would one go about proving these identities? They all follow from the sum and difference formulas. For example, let's look at sine of 2 theta. We'll start with the sine sum formula. Sine of alpha plus beta is equal to sine of alpha times cosine of beta plus sine of beta times cosine of alpha. If we allow alpha to be theta and beta to be theta, then this identity tells us that sine of theta plus theta, or 2 theta, is equal to sine of theta times cosine of theta plus sine of theta times cosine of theta. So as you see, we have 2 times sine of theta cosine of theta. That's where the first identity comes from. The second identity involving cosine of 2 theta, that comes from another sum formula, but that's for cosine. So if we start with cosine of alpha plus beta, the sum formula tells us that this is cosine of alpha times cosine of beta minus sine of alpha sine of beta. So once again, if we choose alpha to be theta and beta to also be theta, then we have that cosine of alpha plus beta, that's theta plus theta, or 2 theta, equals cosine of theta times cosine of theta minus sine of theta times sine of theta, which of course is equal to cosine theta quantity squared minus sine of theta quantity squared. That's this identity. To get the other two, we simply use the Pythagorean identity. First, we could observe, for example, that cosine of theta squared is 1 minus sine of theta squared. And if we subtract sine of theta squared from that, we end up with 1 minus 2 times sine of theta squared. The other option would be to use the Pythagorean identity on sine of theta squared, because then we would have cosine of theta squared minus, and we rewrite sine of theta squared as 1 minus cosine theta squared. Well, minus 1 gives us a negative 1, but minus a negative cosine gives us plus a cosine. So that tells us we have cosine theta squared plus cosine theta squared, which is 2 times cosine theta squared minus 1. And that's this identity. That leaves us with our final identity. Tangent of 2 theta equals 2 times tangent theta divided by 1 minus tangent theta squared. This one is obtained by using the double angle identities for sine and cosine. So for example, we can see that tangent of 2 theta is sine of 2 theta divided by cosine of 2 theta. Sine of 2 theta is 2 times sine of theta cosine of theta. And cosine of 2 theta can be rewritten in a number of ways, but let's use this method right here. We write that as cosine theta squared minus sine of theta squared. Now, why does this help us? Well, now if we divide everything by cosine theta squared, so if we divide the top by cosine theta squared, and we divide the bottom by cosine theta squared, let's put that in brackets, what do we end up with? We end up with 2, let's just move this down a little bit, we end up with 2 times sine of theta, and then we have a cosine theta divided by cosine theta squared. So we're going to cancel cosine theta in the numerator with one of the cosine thetas in the denominator, but that's going to leave 1 in the denominator. What about in the denominator of this expression? Here we have cosine theta squared divided by cosine theta squared. So that's going to give us a 1. Minus, now we have sine of theta squared divided by cosine of theta squared, which is sine of theta divided by cosine of theta quantity squared. But sine over cosine is tangent, so we have 2 times tangent of theta divided by 1 minus tangent of theta quantity squared. And that's how we prove these identities. Let's go ahead and do some examples using these identities. For our first example, we know that sine of theta is 1/4, and we know that theta is between pi over 2 and pi. Given that information, find the exact value of sine of 2 theta and cosine of 2 theta. This information here, that theta is between pi over 2 and pi, is here to tell us that our angle theta is in the second quadrant. So what's the value of that? If you know that you're in the second quadrant, that means you're over here somewhere. That's the second quadrant. So in particular, cosine is negative and sine is positive. We see that sine is positive, sine is 1/4, but cosine is negative, and that's important because we're going to need to know cosine of theta in order to do these problems. We know from our identities that sine of 2 theta, which is one of the things we're asked to compute, is equal to 2 times sine of theta times cosine of theta. We know what sine of theta is, we're told that, but we'll need cosine of theta. Similarly, cosine of 2 theta is equal to cosine of theta quantity squared minus sine of theta quantity squared. So once again, we need to know what cosine of theta is. That's what we need this information for. Of course, we need to still compute cosine of theta, but we can do that using sine of theta and the Pythagorean identity. Because recall that cosine theta squared plus sine of theta squared is equal to 1. So cosine of theta squared is equal to 1 minus sine of theta squared. Well, what is sine of theta? We know that sine of theta is 1/4. So this is 1 minus 1/4 squared, which is 1 minus 1 over 16, which is 15 over 16. So what we have here is that cosine of theta quantity squared is 15 over 16. So cosine itself is the square root of this. Well, it's plus or minus the square root of 15 over 16. But we know that cosine is negative, so that means in this case we want to choose the negative square root. So cosine of theta is equal to the opposite of the square root of 15 over 16, which is the opposite of the square root of 15 over 4. So that's cosine of theta, and we can use that information to compute sine of 2 theta and cosine of 2 theta using these identities. So sine of 2 theta is equal to 2 times sine of theta times cosine of theta. That gives us minus 2 square roots of 15 over 16. Or, if you prefer, the opposite of the square root of 15 over 8. We can also now compute cosine of 2 theta. That's cosine theta squared minus sine of theta squared. Cosine of theta squared, we know, is 15 over 16. And sine of theta squared is, well, sine of theta, remember, is 1 over 4. So sine of theta squared is 1 over 16. So cosine of 2 theta is 15 over 16 minus 1 over 16, which is 14 over 16. And we can reduce this to 7 out of 8. So that gives us sine of 2 theta and cosine of 2 theta. For our next example, we're asked to verify an identity. We would like to show that cosine of theta quantity to the 4th minus sine of theta quantity to the 4th equals cosine of 2 theta. The way that we're going to show this is by first using the difference of squares formula. The difference of squares formula says that a squared minus b squared is equal to a minus b times a plus b. We're going to use this formula with a equal to cosine of theta quantity squared and b equal to sine of theta quantity squared. So let's start by looking at this cosine of theta to the 4th minus sine of theta to the 4th. So we'll start with cosine. So cosine theta raised to the 4th minus sine of theta raised to the 4th. So I'm going to rewrite these as cosine theta squared raised to the 2 power minus sine of theta squared raised to the 2 power. So cosine theta squared quantity squared is raising an exponential to an exponent, so you multiply the exponents together and get 4. Sine of theta squared raised to the 2 power, again, you multiply the exponents together to get 4. That's supposed to be a theta. Let's just make it look more like a theta and less like a 2. There we have it. So now this is our a squared minus b squared. So this is going to be equal to a minus b times a plus b. A is cosine of theta squared, so this is going to be cosine of theta squared minus b, which is sine of theta squared, times, and now it's a plus b, but that's going to be cosine theta squared plus sine of theta squared. Cosine theta squared plus sine theta squared, that's according to the Pythagorean identity, that's equal to 1. And cosine theta squared minus sine theta squared, according to our identity, is equal to cosine of 2 theta. So what have we shown? We've shown that cosine of theta raised to the 4 minus sine of theta raised to the 4 is equal to cosine of 2 theta times 1. But of course that's just 2 theta. So we've shown that the left side of the equation, cosine theta to the 4th minus sine of theta to the 4th, is equal to the right side of the equation. So that means we've verified the identity. Let's talk about the reduction formulas. The reduction formulas tell you how to reduce the exponent on the trigonometric functions. So if you have sine to the 2nd power, you can reduce it to a trigonometric function to the 1st power. Now there are some other terms here as well, as you can see. Now all of these follow immediately from our previous identities. In particular, we want to use our double angle identity for cosine, or our double angle identities for cosine. So recall that cosine of 2 theta is equal to cosine of theta squared minus sine of theta squared. And we were able to use the Pythagorean identity to rewrite these as 1 minus 2 times sine of theta quantity squared, and also as 2 cosine theta quantity squared minus 1. Now it's these last two identities that we want to use. So let me just number them. So I'm going to call this one 1, and I'm going to call the other one 2. So let's start with the identity that we're calling 1. So we have that cosine of 2 theta is equal to 1 minus 2 times sine of theta quantity squared. Basically, the idea here is you just want to solve for sine of theta squared. So what we can do, for example, is we can add 2 times sine of theta squared to both sides, and we can subtract cosine of 2 theta from both sides. Then we'll have that 2 times sine of theta quantity squared is equal to 1 minus cosine of 2 theta. Now it's just a simple matter of dividing by 2, and you have sine of theta quantity squared is 1 minus cosine 2 theta over 2. That's the first identity. What about the second identity? That's going to use what we were calling 2. So we have cosine of 2 theta is equal to 2 times cosine of theta squared minus 1. And again, we just want to solve for one of these trig functions. Solve for cosine theta squared in this case. This one is even easier. You just add 1 to both sides. Then you'll have cosine of 2 theta plus 1 is equal to 2 times cosine of theta squared. Divide everything by 2, and you'll have cosine of 2 theta plus 1 divided by 2 is equal to cosine of theta quantity squared. And that's the second identity here, although it's rewritten a little bit. We just have that cosine of theta squared is equal to not cosine of 2 theta plus 1, but 1 plus cosine of 2 theta. And of course that's the same thing. Divided by 2. Tangent of theta squared is obtained simply by dividing sine theta squared by cosine theta squared. The first of these, the numerator, 1 minus cosine 2 theta squared divided by 2, is divided by the second, 1 plus cosine 2 theta divided by 2. The 2's will cancel, and you'll just be left with 1 minus cosine of 2 theta, which is the numerator, divided by 1 plus cosine of 2 theta, which is the denominator. So I won't write that down. Let's use the reduction formula to do this example. So this example says rewrite cosine of 8x quantity squared so no trigonometric function has exponent greater than 1. So we want to use our reduction formula for cosine. Cosine of theta quantity squared is equal to 1 plus cosine of 2 theta divided by 2. And we want to use this with theta equals 8x. Consequently, we write cosine of 8x quantity squared. So again, theta is equal to this 8x. So we're going to write this as 1 plus cosine of 2 times theta, but theta is 8x, divided by 2. The whole thing divided by 2. And that's going to equal 1 plus cosine of 2 times 8 is 16 times x. And again, everything divided by 2. So we started out with a cosine term squared raised to the 2 power, and we've rewritten it so there is no exponent greater than 1. This is cosine of 16x to the 1 power. That's why it's called the reduction formula, because it reduces the power. It starts out as a power of 2 and ends up as a power of 1. Our next example is similar. Rewrite sine of 2x to the 4th so no trigonometric function has exponent greater than 1. We're starting out now with an exponent of 4, and we want to get it down to something no greater than 1. So let's give it a try. This is sine of 2x, so we want to use the reduction formula for sine. So sine of theta, quantity squared, is equal to 1 minus cosine of 2 theta divided by 2. The only difference between the reduction formula for sine and cosine is that cosine has a plus here, sine has a minus. Okay, in this case, theta is equal to 2x. So we start with sine of 2x. The only problem is that we have a 4 here. So let's rewrite this as sine of 2x quantity squared and raise that to the 2 power. Now we have sine of theta squared quantity squared. So of course, if you raise an exponential to an exponent, you multiply the exponents together to get the 4. But inside these brackets, we have sine of theta quantity squared, and we're going to use our reduction formula on that. So this becomes 1 minus cosine of 2 times theta, but theta is 2x, divided by 2. And all of this is raised to the second power. So we have 1 minus cosine of 4x divided by 2 quantity squared. Let me just fix that bracket a little bit. So we still have an exponent of 2 here. What we're going to do is we're just going to square everything inside the brackets. So this is going to be equal to 1 minus 2 times cosine of 4x plus cosine of 4x quantity squared, and all of this is divided by 2 squared, which is 4. So here we have a 1, that term's fine. Here we have a cosine of 4x. Well, that's okay too, because the exponent here is no greater than 1. In fact, it's equal to 1. But here, this last term is cosine at 4x quantity squared. So we need to use a reduction formula on this. And we're going to use the reduction formula for cosine. But in this case, we're going to let theta be equal to 4x here. So we're going to have that this is equal to 1 minus 2 times cosine of 4x plus, and now here, we're going to use the reduction formula for cosine. So that's going to be 1 plus cosine of 2 theta. But in this case, theta is 4x. And all of this is divided by 2 inside the brackets. And all of this expression is divided by 4. Okay, so just to be clear here, this 4x is our theta, and that's appearing here. So it's 1 plus cosine of 2 times theta, but our theta is now 4x. So this is equal to 1 minus 2 times cosine of 4x plus 1 plus cosine of 8x over 2. And all of this is divided by 4. So we can write this as 1 divided by 4 minus 2 divided by 4, or in other words, this will be 1/2 of cosine to the 4x. So here we're looking at a 2 divided by 4, so that's going to give us a 1/2. And then finally we're going to have plus 1 over 2 times 4 is 8, plus cosine of 8x over 8. So that's supposed to be an 8. Now these 8's here come from this 2 and that 4 both in the denominator. So 1/2 divided by 4, that's 1/2 times 1/4 is 1/8. And so that's our answer. So we were able to use the reduction formulas. We had to use the reduction formula for sine, but also the one for cosine in order to reduce this sine of 2x to the 4th. So it was in terms of trigonometric functions having exponent no greater than 1. This leads us to our half-angle identities. The half-angle identities are exactly the same, essentially, as the reduction formulas, just with slight changes. So, for example, we have that sine of theta over 2 is equal to plus or minus the square root of 1 minus cosine theta over 2. This comes from the reduction formula for sine. We know that sine of theta squared is equal to 1 minus cosine of theta, 2 theta, divided by 2. So what we do is we replace theta with theta over 2. Just everywhere that you see a theta, just replace it with theta over 2. So you'll have sine of theta over 2 quantity squared is equal to 1 minus cosine of 2 times theta over 2 divided by 2. Now that 2 will cancel with that 2, and you'll have that sine of theta over 2 squared is equal to 1 minus cosine of theta over 2. Essentially what the reduction formula is telling you is that if you have sine of theta raised to the 2 power, you can rewrite it in terms of this cosine, but you just have to double the angle. So if instead of theta you start with theta over 2, then when you double the angle you end up with theta. But you're just doubling the angle to get that theta. Next we compute the square root of both sides. So sine of theta over 2 quantity squared is equal to 1 minus cosine theta over 2. So that tells us that sine of theta over 2 is equal to plus or minus the square root of 1 minus cosine theta over 2. And that's exactly our first half-angle identity. I won't work through the other two, but it's the same idea for cosine of theta over 2 and tangent of theta over 2. You start with the reduction formula, replace theta with theta over 2, and then just compute the square root of both sides. Let's go ahead and use these identities to compute some values. Here's our first example. Find the exact value of sine of pi over 12. We're going to use our half-angle identity to solve this, and we want the half-angle identity for sine. So if we just go back to remind ourselves what the half-angle identity is for sine, sine of theta over 2 is equal to plus or minus the square root of 1 minus cosine of theta over 2. So for this one, we have that sine of pi over 12 is equal to plus or minus the square root of 1 minus cosine. And so whatever the angle is, you just double it. So it's going to be 2 times pi over 12 divided by 2. So that's plus or minus the square root of 1 minus cosine of 2 times pi over 12, that's pi over 6, divided by 2. Now we have to figure out whether this is plus or minus. Now pi over 12 is in the first quadrant. So if we draw our little unit circle, pi over 12 is in this quadrant. So that means sine and cosine are both positive here. So what that means is we want the positive square root. So sine of pi over 12 is equal to the positive square root of 1 minus cosine of pi over 6 divided by 2. Now cosine of pi over 6 is something that we know. Pi over 6 is 30 degrees, so that's this angle. And this has coordinates square root of 3 over 2, comma 1/2. So cosine of pi over 6 that's the x-coordinate, so it's square root of 3 over 2. So this is equal to the square root of 1 minus the square root of 3 over 2 divided by 2. So sine of pi over 12 is equal to the square root of 1/2 minus the square root of 3 over 4. Or if you prefer, you can write this as the square root of 2 minus the square root of 3 over 4, if you want to give them a common denominator. Now, another way to write that would be the square root of 2 minus the square root of 3, and all of that divided by the square root of 4, which is 2. All three of these are the same thing, just written in a different way. Here's another example. Find the exact value of sine of 7 pi over 8. Again, we want to use the half-angle formula for sine. So, sine of 7 pi over 8 is equal to plus or minus the square root of 1 minus cosine, and now we just double the angle. So it's going to be 2 times 7 pi over 8. And all of that divided by 2. And that will be equal to plus or minus the square root of 1 minus cosine. So 2 times 7 pi over 8 is 7 pi over 4 divided by 2. All right, well, again, we need to figure out whether this is positive or negative. And in order to do that, we need to figure out what quadrant 7 pi over 8 is in. So we draw the unit circle. Seven pi over 8 is just a little bit smaller than 8 pi over 8. Now 8 pi over 8 is pi. So 8 pi over 8 is right here. So 7 pi over 8 is going to be in the second quadrant. So that means x is negative, but y is positive. So that means we want to choose the positive square root, because we're computing sine, which is the y value. So this is going to be positive. Okay, so that tells us that sine of 7 pi over 8 is equal to the positive square root of 1 minus cosine of 7 pi over 4, and all that divided by 2. The next thing to do is to figure out what cosine of 7 pi over 4 is. In order to do that, it will help to figure out what the reference angle is for 7 pi over 4. So 1 pi over 4 is here, 2 pi over 4 is here, 3 pi over 4, 4 pi over 4, 5 pi over 4, 6 pi over 4, 7 pi over 4. 7 pi over 4. Is that angle. It probably would have been easier to think about it in the other direction, because this is 8 pi over 4. So 7 pi over 4 would be 1/4 of a pi clockwise. Anyway, so that tells us what our reference angle is. Our reference angle is pi over 4. The coordinates here are square root of 2 over 2, comma square root of 2 over 2. That tells us what the coordinates are for 7 pi over 4. Because the numbers are the same, except you might have a negative in front of something. Well, the x-coordinate is the same, square root of 2 over 2, but the y-coordinate has a minus there, square root of 2 over 2. On the other hand, we're looking at cosine of 7 pi over 4. That's the x-coordinate. So what we're looking for is square root of 2 over 2. That's what goes in here. Square root of 2 over 2. So that tells us that sine of 7 pi over 8 is equal to the square root of 1 minus the square root of 2 over 2 divided by 2. We can simplify this. Sine of 7 pi over 8 equals, so what is this? This is going to be the square root of 1/2 minus the square root of 2 over 4. Or if you want to give those a common denominator, that will be 2 minus the square root of 2 over 4. And the square root of 4 is 2, so we can write this as the square root of 2 minus the square root of 2, all divided by the square root of 4, which is 2. And there's your answer. For our next example, we'd like to verify an identity. So how are we going to do this? Well, we'll start with the more complicated side on the right, and we'll use our identities to see if we can rewrite this as tangent of theta. So that's our objective. So we'll start with 1 minus cosine of 2 theta, and that's divided by sine of 2 theta. So cosine of 2 theta we can rewrite as cosine of theta squared minus sine of theta squared. Sine of 2 theta we can rewrite as 2 times sine of theta times cosine of theta. Okay, well, what do we want to do from here? Well, our objective is to get a tangent, which is sine over cosine. So here's a cosine right here. So the question is, can we get a sine in the numerator? Well, actually what we want is we want more than one sine, because we've got a sine here. So what we would really like is to get sine theta squared up here. So that way we can get rid of one of these signs, and then we'll be left with sine over cosine. And I can see exactly how to do that, because I have a 1 minus cosine theta squared. Let's just rewrite this so we don't have any brackets. So this is 1 minus cosine theta squared. Minus a minus is plus sine of theta squared, divided by 2 times sine of theta cosine theta. And now we notice that we have a 1 minus cosine theta squared right here. 1 minus cosine theta squared. By the Pythagorean identity, this is equal to sine of theta squared plus sine of theta squared over 2 times sine of theta cosine of theta. So this sine of theta squared is the same as 1 minus cosine theta squared, so that's where that one comes from. But now we have sine of theta squared plus sine of theta squared, which is going to give us in the numerator 2 times sine of theta squared. And in the denominator we have 2 times sine of theta times cosine of theta. And now we have everything that we need. So this 2 will cancel out with that 2. The sine of theta in the denominator will cancel out with one of the sine of thetas in the numerator. And you're left with sine of theta divided by cosine of theta, which is tangent of theta. So 1 minus cosine of 2 theta over sine of theta, which is the right side of the equation, is equal to tangent of theta, which is the left side of the equation. So we've just verified the identity. Here's another identity. This is, I guess you could call it a triple angle identity, because here we have sine of 3 theta, and we want to rewrite it in terms of thetas. So how are we going to do this? Well, we start with a sine of 3 theta, so let's write that sine of 3 theta. Let's write this as sine of theta plus 2 theta. So what we've done is we've written sine of 3 theta is sine of theta plus 2 theta. So now it's an addition formula. We have the sum of two angles. So we can use the sum formula for sine. So this will be sine of theta times cosine of 2 theta plus cosine of theta times sine of 2 theta. So now we have some thetas here, but we still have a 2 theta here and a 2 theta here. So what we'll do is use the double angle identities here on cosine of 2 theta and sine of 2 theta. So sine of 2 theta we know is 2 times sine of theta times cosine of theta. And what about cosine of 2 theta? Because there are a few different ways to write that one down. Well, let's just try cosine theta squared minus sine of theta squared. If this version of the identity doesn't give us what we want right away, we'll just use the Pythagorean identity in some way to adjust it. But let's see if this works. So far we have sine of theta times cosine. I'm just rewriting what we have here. I'm just rewriting it all on one line. Plus cosine, everything that's in green I'm just writing in brackets. 2 times sine of theta times cosine of theta. Okay, let me just fix that bracket. There we go. So let's distribute. By the way, there's a theta here. That's cosine of theta. Okay, so let's distribute the sine. So we're going to have sine of theta times cosine theta squared minus sine of theta times sine of theta squared is going to give us a sine of theta cubed. Plus, and now we distribute this cosine. So we're going to have 2 times cosine times sine times cosine. That's going to give us sine of theta times cosine of theta squared. Okay. So we're getting there. Notice now that we have a sine of theta times cosine of theta squared here, and we have 2 of those same things here. Sine of theta cosine theta squared and 2 times sine of theta cosine theta squared. So we're going to combine those, and that'll give us 3 times sine of theta times cosine of theta squared minus sine of theta cubed. And now we're going to use the Pythagorean identity like we suggested we might want to do. So cosine of theta squared is 1 minus sine of theta squared. So that gives us 3 times sine of theta times 1 minus sine of theta squared minus sine of theta cubed. And I didn't mean to put that in gray, so let's just convert that to blue like the rest of this. Okay. Now notice we've gotten rid of all of the cosines, and that's one of our goals. We have sine of 3 theta. We want to write that as 3 times sine of theta minus 4 times the quantity sine of theta cubed. But there are no cosines here, but we've gotten rid of all of the cosines. So the next step is to distribute the 3 sine of theta. 3 sine of theta times 1 is just 3 times sine of theta, minus 3 times sine of theta times sine of theta squared is going to give us 3 times sine of theta cubed, minus sine of theta cubed. Now we see that there's a 3 sine of theta cubed and a sine of theta cubed. Both of them have a minus in front. So that means we have 3 times sine of theta minus 4 times sine of theta cubed. And that's exactly what we wanted to show. We wanted to show that sine of 3 theta was equal to 3 times sine theta minus 4 times sine theta cubed, which is right there. And that's what we've shown.